Welcome everyone to the BioPhotonics Microscopy Summit. In this session, you will hear from Ingo Riemer, the Chief Technology Officer at APE. Ingo has over 20 years of experience working on light sources for coherent Raman microscopy and joins us today to highlight some new developments in light sources for ultra-sensitive stimulated Raman scattering. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch them on demand. That's all from me. Ingo, we appreciate you for taking the time to join us at the Microscopy Summit.
Thank you, Jake, for the introduction. And I'm happy to be here. And it's actually my very first webinar. So I hope it goes well and I hope you can enjoy it. So, well, as Jake already said, I'm talking about stimulated Raman microscopy imaging. And we do have a new light source at APE, which is called the picoEmerald FT. And I want to compare the old and the new stuff. And I think the results are pretty cool. But before I want to start on that, I want to give you a brief introduction of the company I work for. The company is called APE, which is Angewandte Physik und Elektronik GmbH. It stands for Applied Physics and Electronics GmbH. So we are manufacturing devices for characterization and modification of ultra-short pulses. We are serving the research market, universities, and research institutes worldwide, as well as the industry. We are not really new. We are not newcomers. We are around for the last 33 years. You can see the founders of the company on the top here, and well, it's still a family-owned business, and they're happy to work in the company. And yep, we have a long history. We have a company in the US, which helps us, and otherwise we are based in Berlin, in Germany, and that's where all the production takes place. In the meantime, we have 65 people here in Berlin, 4 people in the US. We are having 17 R&D and production labs, 3 clean rooms. About 30% of our expenditure is going back into R&D, with about 20 engineers in physics, software, and mechanical design. And all the manufacturing is happening in Berlin. So what are we known for? Well, we are the global market leader for ultra-fast laser diagnostics. Autocorrelators, probably many people know us for. These are the small blue boxes, probably standing next to every second femtosecond laser. And well, if you want to have a tunable laser, then you just get a fixed frequency laser and put an OPO behind, as long as it's mode locked. We're having more than 1,000 of these in the field. And we do lots of customized stuff, so please talk to us. And well, because of the tunable OPOs, this is basically also the topic I just want to jump into. And so that's why I want to talk about, well, SAS imaging, because for that you need tunable light sources. Therefore, now start the real presentation, talking about stimulated Raman imaging. So, stimulated Raman imaging, I don't know how much you're all familiar with this technology. So therefore, I want to step back a bit and talk about Raman scattering. What is Raman scattering? Well, that's inelastic scattering of light. Basically, you're shooting in a photon and you're just getting a photon with a different color back. Typically, it's redshifted. So it's a Stokes shifted process, and you're exciting a vibrational band. A different way of looking into it is basically what you're just exciting a virtual state, and from there, a light is emitted to excite or to populate a vibrational state. The difference between the pump and the Stokes is equivalent to the excited level, the vibrational energy. And well, you can record all that. You can take a whole spectrum, and what you get out is a spectrum of all the vibrational bands of the molecule you have. An example on top is benzoic acid. So all these nil nines you can get. Unfortunately, this effect is very weak and inefficient, so it takes a while. And if you want to do imaging, it is extremely slow. So how to speed it up? You can speed it up by just not only having a pump beam to the virtual state, but also a beam which is equivalent to the energy of the Stokes pulse. If you do that, you're basically pushing all the photons, you're stimulating that kind of transition. And when you want to do imaging, that actually gives you a 3 to 5 orders of magnitude faster imaging. So you now can go up to video rate imaging with stimulated Raman, which is, well, from millisecond to microsecond range when you want to do standard Raman. So it's a huge improvement. Secondly, what you already can see on the scheme, it is a two-photon process. You need short pulses for it. So like your two-photon fluorescence, that is pretty much comparable. And also there, the interaction basically takes place in the focus. That means you do have intrinsic 3D capability, which is again a huge improvement in comparison to standard Raman. And you can really compare it with two-photon fluorescence in comparison to standard fluorescence. So what do we have to take care of? So how do I detect such a signal? As I already said, we are stimulating the transition between pump to Stokes. So, and I have lots of pulses. So I have my pump pulses, a pump pulse train, and always when the Stokes pulse train is switched on, and they're all overlapped in space and time at the sample site, that's a precondition. If they're both there, then I get the energy transfer from pump to Stokes. If the Stokes is switched off, I just only get Raman scattering, so it's basically no transition, more or less. And so I get what if I switch it on and off, I basically get this transition or just don't have a transition, and I get a stimulated Raman loss in the pump beams. Basically energy change or change in power in the pump beam. If I just have a detector behind my sample, I will see an intensity modulation depending on the modulation frequency of my Stokes. Then I put a lock-in detection behind and I'm done. Unfortunately, the signal is extremely small. I'm looking at 10 to minus 4 to 10 to minus 8 changes in the signal intensity. So that already gives me an idea what I have as a pre-requirement on the laser source. The laser source needs to be extremely low noise. And I have to have enough power on the sample and on the detector to beat shot noise limit. Of course, I don't need I can't allow for too much power, then I burn the sample. So it's always a gamble what's the best mixture is. Just to give you more ideas how the signals are generated, I just give you a few formulas. I just want to ensure you there are not that many formulas. It's the only one here in the presentation. So the signal strength is proportional to the pump power, the Stokes power, the pulse length, and the repetition rate. So if you think of, well, it's indirect proportional to the pulse length, I just can go to femtosecond, I'm easy. But unfortunately, I have a certain bandwidth of my vibrational lines, which are typically in biological samples, something like 10 wave nimbus. So if I have a 100 femtosecond pulse, that's 100 wave nimbus, so they don't interact. So I have to work in the picosecond regime to excite them efficiently. So much shorter than a picosecond doesn't work. So 1-2 picosecond would be ideal. Repetition rate, I want to image fast. I want to do microscopy imaging. So I have to be in the multi-megahertz range. So mode-locked lasers would be ideal. 80 megahertz, 40 megahertz, maybe 20 megahertz. That's the range people talk about when we are talking about imaging. It's about the same repetition rate as I have them for two-photon fluorescence microscopy. Short note on the signal-to-noise definition. The signal-to-noise definition I'm using here is the intensity squared divided by the variance. I'm using this definition because this is inversely proportional to the integration time, the pixel integration time I need. So basically, signal-to-noise improvement of a factor of 10 means 10 times faster imaging. So another step to explain you what kind of lasers I need for stimulated Raman. Of course, well, I need two colors. I already explained that. And well, these two colors should be tunable because I have to address the vibrational bands independently. Of course, there are other schemes with broadband, narrowband, and spectrometers. I'm not going into that. They're much more complicated and have other problems. So I'm talking about picosecond because I think we do believe at APE in picosecond SIS microscopy. So vibrational line width is something like 10 wave numbers, and that translates into about 2 picoseconds. And of course, well, picoseconds or femtoseconds do work. Femtoseconds, you can do spectral focusing, another technology with mode-locked lasers to go to narrow band excitation, but that comes with its own challenges. So therefore, I'm just really looking into pure picosecond systems. And why do we talk about laser plus OPO, optic parametric oscillators? They are inherently jitter-free, so they're optically synchronized. Because in the end, you have to have an overlap, a perfect overlap of pump and Stokes at the sample site in space and time. And if there's any jitter between pump and Stokes, it's noise in the image. You have to have high output power. High output power, ideally a few hundred milliwatts, because you have a lossy microscope, you just want to overfill your objective, and many other things. And the system needs to be very low noise, ideally short noise limited. So what's the history of coherent Raman microscopy? In 1999, Andreas Sumbusch, Gary Holtam, and Sunny Shi published the first paper on coherent anti-Stokes Raman scattering microscopy. I have to point out microscopy because, well, CARS has been invented in the 60s. So, but they were the first people just implementing it into microscopy. 5 years later, already APE jumped in and had still a bit bulky setup to provide a laser plus OPO to do coherent Raman microscopy, and that was much better and more suited than any electronic synchronization of lasers, which were used before. In 2009, we already started packing everything into one box. That was the so-called picoEmerald. In 2015, we shortened the pulses from 6 picoseconds to 2 picoseconds. I showed you the equation that from 6 to 2 picoseconds, that should gain a signal strength in a factor of 3 for SIS. And that what we also could prove at the time. And well, what happens now? We now have 10 years later, we have a new light source. And that's what I want to talk about now. And I want to concentrate on comparing the new light source with a light source we had 10 years ago. So, what is coherent Raman microscopy or SIS all about? It's about sensitivity. You want to have, you want to image the whole vibrational spectrum. So you don't want to only image CH2 or CH3, which is always the strongest line, which are around 2800, 2900 wave numbers. You also want to image substances at low concentration, such as drug distributions. And you can see in the spectrum, these are typical spectra in this case of tissue, muscle, and skin. In the fingerprint range between 500 and 1500 wave numbers, all the vibrational bands are much weaker than the CH2 or CH3. This is therefore much more difficult to image them. Of course, well, imaging of fingerprint region and or even of Raman labels have been done in the past, also with the old system with the picoEmerald S, but there's always room for improvement. So what we want to do is fast tuning, and we want to have a better sensitivity. These are the two main goals, and I want to show you what we have achieved. So I'm just giving you a table. Looks a bit boring, but I'm just leading you through that. So with the picoEmerald as the old model, when going from one vibrational band to the other, if you have a random access, say just you want to change the wave numbers by 500, then it took something like 60 to 120 seconds, quite a while. There was a kind of fast tuning mechanism when you want to sweep through a spectrum. But even that took 5 to 10 seconds per wavelength step. Now we achieve something like 1.5 seconds. That's up to 100 times faster tuning. We changed the repetition rate from 80 to 40 megahertz. 40 megahertz is still fast enough to do a proper video imaging, but reducing the repetition rate by a factor of 2 gives you a 2 times higher SAS signal, or even 4 times higher cast signal. The modulation frequency now is at 20 megahertz as it was before, but now 20 megahertz is exactly half of the 40 megahertz. It's phase locked to the 40 megahertz. And that actually gives you now a positive interference of the 20 megahertz and the heterodyne signal, basically doubling your SAS signal, and you're getting a 2 times better signal to noise. The pulse length is about the same, slightly shorter than before. We achieved the same bandwidth, which was important for getting the spectral resolution. Short noise limiting is very important. I explained that to you. And we expanded the tuning range a bit. We came from 410 to 4,600 wave numbers to down to 210 wave numbers, up to 1,000, well, 5,400. You can do other things with that. They're up there. There are no vibrational bands anymore, but you can tune down to 660 nanometers, which is already nearly orange if you just like colors. Otherwise, you're working in the near infrared. Power, output power. As already said, it is always good to have enough power. Some people just send in something like 50 milliwatts at the sample site, which is a lot for many samples. But if you have your microscope objective optimized for other modalities and not the highest throughput, or if you just want to overfill your back aperture, then having a factor of 10 in headroom is always a nice thing to have. So therefore, we are providing 500 milliwatts plus in the OPO output power, and everything is automatically attenuated, and the power control is included. So if you want to work at 150 milliwatts throughout the range, you just pinch in that in the software, and it always stays at 150 milliwatts. The same is true for the Stokes beam, by the way. So noise levels. I already talked about the relative intensity noise. You want to be short noise limited. Where do you want to be short noise limited? At the frequency where you want to detect. We are modulating at 20 megahertz, so we are detecting at 20 megahertz. So the noise level at 20 megahertz is important. Compared to the old system, we were already at short noise limited at 20 megahertz. You can see here. This is measured at 10 milliwatts. And now the new system, you can see again, we are short noise limited. That's the blue curve here. But also when you follow the curve, the blue curve, now we just get the 1 over F above 1 megahertz. We get the 1 over F fall in the noise. But then we are hitting the short noise floor. Probably if our measurement technique would have been more sensitive, we probably could be able to go to higher power, and even the short noise limits is probably even lower than the minus 161 dB. So we are all fine. We don't need any kind of balanced detection, any kind of detection tricks. We just can send it directly on a photodiode, amplify it, going to a log-in amplifier, and we are done. The whole system comes with an easy-to-use graphical user interface. You pinch in the wavelength or wave number you want to have, power levels, and the delay between the pump and Stokes. Everything we are taking care of. So it's basically really set on really a system where you just completely hands-free. Everything is completely computer controlled. You can write your program from your microscope, for instance, through using a TCP/IP interface we provide. So integration into the software is done within a few hours and you are done. Well, coming to measurements. What you now see here is a comparison between spontaneous Raman and stimulated Raman microscopy measurement, just taking a spectrum of DMSO. So the orange line you can see is the spontaneous Raman spectrum, where we basically only did background correction, no intensity scaling, only at, well, the intensity scaling was happening only at one position. And then you can see all these spectral peaks are shown in both graphs, and the intensity is also exactly the same. So it shows the system is very reliable. Just you're having your Raman spectrum, you're having your SAS spectrum, they are the same. So that's great. And now I just want to compare the improvement in signal to noise quality. For that, we basically hooked up the old laser, the picoEmerald S, and the new picoEmerald FT behind the same microscope. And then we just looked at the same samples, doing it basically sequentially so that we can be sure, looking at the same samples and comparing them. And I will show you the results. Well, doing something very boring at the beginning, we are taking rapeseed oil. So no structure at all, just looking at signal strength, looking at the CH2 signal strength. We are now taking basically 25 images, doing statistics over 200 by 200 pixels. And with all that, we realize we get a signal to noise increase by a factor of 10. That was about to be expected, slightly higher because we're having slightly shorter pulses. So that's great. So that should, in theory, give us 10 times faster imaging for the same power levels. And so let's see whether 10 times faster imaging is possible. So we used onion skins in this case. Again, starting with CH2 because it's a strong line, it's easy to image. So we took the old system, the picoEmerald S with 80 megahertz, and we started off with 2 microseconds. Then we increased the pixel integration time to 20 microseconds. So you see a large increase in signal to noise. Then we switch to the new system, the picoEmerald FT. Do the same imaging at 2 microsecond pixel integration time, so meaning 10 times faster. And the signal to noise ratio is pretty much the same between the 2 microsecond and 20 microsecond. And when I'm just going to 20 microsecond on the picoEmerald FT, I just, of course, get even better signal to noise. Zooming in makes it even more pronounced. And so we just jumping to 880 wave numbers in the middle of the fingerprint region, a very weak band. So you already can see at 2 microsecond with the old system, well, it's extremely noisy. Switching to 20 microsecond, the image quality is good. Again, doing the comparison with the new system at 2 microseconds, same image quality. And well, increasing it to 20 microseconds, of course, it goes up. Zooming into that basically amplifies everything, but gives the same result. We can get really 10 times faster imaging speed. Okay. And then I want to come to the fast tuning. So as I already said, we just want to profit from the fast imaging speed. Beforehand, well, we now can image 10 times faster. But if it then takes a minute to go to a different wave length range, to a different wave number, then it would be kind of a pain. And well, we wouldn't really gain from that. As I already said, we just really speeded it up. And I'll just show you this real-time video. And it should start now. Yeah. So it's about 2 microsecond pixel integration time, 100,000 by 1,000 pixel. So it's 2 seconds to take an image, 1.5 seconds to jump to the next image, taking another image, and so on. So doing stacks of different vibrational bands is very easy to do, very fast. Maybe I can just play the video again. So you see 2 seconds to take the image, 1.5 seconds to go to the next vibrational bands. So it's CH2, M81, CH3. And then I get to that, to the composite image. Okay. So what else you can do? This is actually a pretty easy experiment that was done at the Leica R&D lab. But I think it's very impressive because it shows the capability. This is Drosophila embryos, basically switching between imaging of CH2, that's the lipids, CH3, it's the proteins, and at the same time imaging second harmonic. And on the top left side, you do have the overlay, which you can see. That was done in this example over 45 minutes. So they've later done images, the same loop over 2 hours, and the embryos didn't mind at all. So they were happy all the time. And I also mentioned that the technology is 3D capable, the same as it is two-photon fluorescence. So this is a 3D stack over through a Drosophila larva. And it is very fast to do. So I think Leica it took them something like 2 days to record all these data after they started working with the system. So it's very fast integration and getting the images. What also is possible, talking about fast tuning, doing spectral stacks. So again, Drosophila larva, just taking it, scanning through the CH band and scanning through the fingerprint region, then choosing a region of interest, like up here or here or here, and then you get a spectrum on basically of every region of interest in your image. And that really looks like proper low noise images of the whole spectra. What else can you do? Well, we were talking so far about intrinsic vibrational bands, but sometimes labeling is important. Normally, coherent Raman microscopy is promoted as being not of being label free. But well, looking into metabolism, for instance, you can feed your sample, for instance, with a D2O, and then you can see that is incorporated into CD2, CD3, and that's what we are going to image to see the vibrational bands of CD2 and CD3 there appearing in the so-called Raman silent region. And you see with low concentration or no concentration of D2O, you basically only we take the ratio between CD and CH and the protein band and the lipid band. That's only basically a little bit of background you can see here. And with 50% D2O, you see the D2O concentration raised a lot, and it is easy to image the difference here. Other things of labeling is, for instance, alkyne detection. What are alkynes? Alkynes are CC triple bonds. They again appear in the Raman silent region around 2100 wave numbers. And one very popular substance is EDU, because that incorporates into the DNA. So the Min lab at Columbia University, they were basically growing HeLa cells in EDU, in this case into 100 micrometers. On the right-hand side, you see basically a spectral scan over the band of the alkyne band, and on the left-hand side, you see the difference between the background and the peak of the EDU. And you can clearly image that. That was very easily done with a pretty short pixel integration time, and the quality was pretty good as well. So that was at 100 micromolar EDU. So they really tried to push it further, and even tried to do the incubation in only 10 micromolar EDU. And even then, you can get clear images. Of course, it's a bit more noisy, of course, but even the power levels were a bit lower, but therefore the pixel integration time a bit higher. We could see EDU even at 10 micromolar incubation concentration. And I was very happy when I saw these results. So, as you've seen, there were results from many different groups, and I'm happy to have them. So first of all, that was the EF Nano in Göttingen, which just helped us with the development in a European Union project. That was Leica Microsystems, Columbia University around Wei Min, KTH and Karolinska Institute in Stockholm. They all provided input and gave us feedback to make this system nice. So I want to conclude with this. What have I shown you? First of all, I showed you a new coherent Raman light source, which is completely hands-free and remote controlled. It shows 100 times faster tuning and 10 times faster image acquisition in comparison to the predecessor. It is really true-shot noise limited, so no balance detection for SLS is needed. They give you real Raman spectra, which I have shown you comparing it with on DMSO. It is fast and easy spectral scans over the whole wavelength range, including the fingerprint range. And we showed imaging of CH regions, lipids and proteins, which is pretty straightforward. Fingerprint region, Raman tags such as CD and alkynes. And for that, I just want to thank you for your patience and thank you for listening.
Thank you so much, Ingo, for highlighting some advances in multispectral SRS imaging. To everyone that's joining us in the audience, if you haven't already, you can type your questions and comments into the Summit chat box, and do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we hope you're enjoying the inaugural BioPhotonics Summit. Thank you all so much for joining us.